We didn't know what was going on. And at some point, my boss, who was the chief engineering, and I was the second there, said, we got air for about an hour and a half more. That means in an hour and a half...
We're losing propulsion.
We're not losing propulsion. In an hour and a half, we lost propulsion.
Oh, wow.
There's no more propulsion in an hour and a half. And in those narrow straits that you're sailing, that means you're crashing somewhere.
Welcome to the Collaborative Podcast. I'm your host, Spencer Krause. Our guest today is Peter Roberts. Peter is a postdoctoral research associate at Carnegie Mellon University and a very good friend of mine. Peter, welcome to the pod.
Well, thank you, Spencer. Thank you for having me here.
Thank you for being here. So what is your research about? Like, what are you working on? What's some of the stuff you're trying to bring into the world?
Well, I'm working in a field that's called haptics. That it's basically all the feedback, but physical feedback that you can get from let's say, for example, a virtual environment or a machine working. How do you feel with this robots are feeling? Very simple thing, like your cell phone vibrating, that's haptics. I know many of you might have the vibration off on the cell phone because it might be annoying sometimes, but...
Oh, it definitely is.
Yeah, definitely. I have it off too. But that's the concept of haptics, like having those physical feedback that's actuating on your body, giving you this information from what's happening on a virtual environment, on a robot that's working like miles away from you. That's what I'm doing. But that's the general description of the field. But specifically what I do, I work with tactile feedback. We're trying to develop interfaces that will provide your hands with active feedback on, for example, a robot that's touching and manipulating objects away from you. And one day you'll be able to feel what the robot is doing, the textures it's feeling, the objects it's touching, if it's compliant, if it's soft, if it's hard, if there's slip, for example, like the things are falling from your hands. All those sensations will be provided to a user at some point.
So how do you convey that stuff to the user? Like, what's the feedback mechanisms that you're looking at?
Well, there's a lot of feedback mechanisms we're using. Like, first the thing, you need to understand how the receptors on your hand work. And they're based on pressure, on frequency, on how you stimulate these receptors. And using different forms of actuation, like pressure, like stretching the skin, putting normal force, shear forces, like how are you stimulating these receptors on the hand to generate sensations that recreate the actual sensations that you feel in your hand when you're manipulating objects.
So can you give me some examples? Like you talk about shear force. When would you want to experience that?
Just picture yourself opening a jar, for example.
Okay. Yeah.
Imagine just a very tight lid. You're putting your hands, one hand's holding the jar, the other one's holding the lid.
That is shear force.
You start twisting, and this lid is super tight, so your hands start slipping on the jar. That's shear force because your skin is deforming on the direction that's opposite to the motion of your hands. But you'll reach a point when your skin will stop slipping, and you'll actually be able to move the jar and open it. So that shear force stopped. There's no more slipping. There's actually a normal force now that is helping you grab the lid and then open it.
Yeah. Well, the normal force was there to begin with, but
it was not enough for you to be able to perform the motion.
Yeah.
Or think, for example, when you're holding a cup, you're filling the cup with water. Let's figure out you're putting it very slowly on it. The cup will, at some point, your grasp won't be enough to hold the cup because the weight of it is increasing. So your skin will start stretching towards the direction, and at some point it will start slipping, but you will try to grab it and hold onto it so it doesn't fall. So all this feedback that you're getting from these objects, we're trying to provide a way that a human can feel this in, for example, a robot that's performing these actions.
Yeah, it makes a lot of sense, actually.
Well, that would be a great thing to do, for example, for teleoperation, or just imagine prosthetics.
Yeah.
Right now, the feedback that a user has from this prosthetics is just purely visual. Like, oh, I see this prosthetic hand holding something, so I know it's holding it. But what if we can recreate those sensations and stimulate, give a neural stimulation so that the person can actually feel what it used to feel
You'd
to
probably
grab
be much
things.
more effective as an operator of that prosthesis.
Definitely.
Yeah. That's cool.
Oh, yeah, definitely. It will be game-changing. And not just thinking of a manipulator or as a user, but also think about a robot hand. Today, robot hands work mostly based on kinesthetic feedback or normal forces, on how much force am I exerting on an object to be able to hold it. But when you hold a pencil in your hand, you can just make it move around your fingers in some way. Or think about like knitting, like all this very subtle motions that help you create this wonderful art with just by knitting. Today, a robot cannot do it very reliable. I know there's some robots that create wonderful things, but the dexterity that the human hand has not yet been achieved, mostly because of this tactile perception that we have, that it's incredibly complex. And we hope at some point provide robots with some sort of sensations or sensing that will provide them this ability and increase their dexterity.
So what are some of the ways that you're doing that in the lab?
Well, right now we're studying the tactile perception, understanding how humans perceive sleep, how this your hand understands the slipping through your fingers, how do you perceive textures, for example, how do you generate this stimulation in different parts of the finger that can recreate textures. Understanding how the human perceives the environment through their skin, that's one of the biggest points here. Once you completely understand this, you can say, okay, now we can take all these understanding, all this data, and provide a robot with a framework that will somehow help him understand the environment as we do.
Yeah. That makes a lot of sense. Easier said than done, I think.
Oh, definitely. It's not an easy job. I mean, no jobs in robotics are easy. Like there's a lot of complex stuff going around, but
it's the easiest thing in the world. What are you talking about?
There's so many people doing it. It's very easy.
Yeah.
But no, it's a nice challenge to address right now.
So, what are some of the interesting robot form factors that you've seen, I guess, at the university, but then also just like around the world?
Oh, it's a very good question. I'd say going back to the same subject we're talking, hands are very interesting. Not just the form factor, but the whole concept of a robot hand is great. Like if you think about like how robot hands looked just a few years ago, it was just a gripper that would hold things between two end effectors that would compress it until it hopefully didn't break. But how this has evolved and how it's being used today, and all the different alternatives to hands. Like I would say there's mainly two different approaches. One is the anthropomorphic hands that resemble human hand with more or less fingers. I've seen hands with more fingers than the human hand and hands with less fingers, but basically all doing some sort of grasping and holding similar to the human hand. And on the other hand, you have like this task-specific grippers that are designed to the specific task. It's still a hand, but it doesn't look like a human hand, but it performs and it's focused on one specific, or sometimes more than one, but a specific task to be performed.
Interesting. Like, give me an example of one of those.
Well, the gripper, like there's two opposing things that compress.
Sure, but that's not task specific.
It's task specific because you're holding something. It's just meant to hold something.
Yeah.
So it's task specific. You may see for example, this pneumatic grippers, like they're like they look like tentacles and use air pressure. They curl around something to hold it. But this curl around something, it's compliant to the object. It's not like the human hand that we always curl in a certain way. But this one completely adapts to the object that you're holding.
Yeah.
Like with, I won't say the number because it's many degrees of freedom that this flexible tentacle provides the
Infinity.
hand. But definitely it's just for holding something.
Yeah. Is it infinity degrees of freedom, or is it 2 degrees, like 1 degree of freedom?
That's a good question. There's different approaches, but
But if the only input is air and it can just do this, like, is that 1 degree of freedom, or because there's so many different positions and orientations, is that infinite degrees of freedom?
that's the thing. If you're thinking just about the input from the air, you could say, okay, it's just 1 degree of freedom because it's air pressure. You're just providing this specific amount within a range, which will give 1 degree of freedom. But that's because of this variable. But when you think about the actual
The output.
task
Yeah.
being done and how this hand conforms around the object and how it interacts with the environment, those are infinite degrees of freedom.
Yeah.
It's like the elephant's trunk.
Yeah. The elephant's trunk only has 1 input.
I don't know if it has more than one input, but it's just neural stimulation to move those muscles. But it can curl around anything.
Yeah, for sure. Yeah. Sorry, getting philosophical on the definition of degrees of freedom here.
Oh yeah. Oh, we can go down this rabbit hole for a long time.
I like rabbit holes. That's like one of my favorite parts of podcasting is going down these rabbit holes. This episode of Collaborative with Spencer Krause is brought to you by Rockwell Park. If you're building something in tech, robotics, AI, or even advanced manufacturing, Rockwell Park is already home to companies just like yours. Located right here in the historic East End of Pittsburgh, Rockwell Park has spaces starting at 1,000 square feet all the way up to over 100,000 square feet. So if you're an early-stage startup or even a Fortune 500 company, here you can scale without limits. Look, we built this studio in Rockwell Park. We love working with these guys. You should check them out. If you're interested, go to rockwellpark.com. Collaborative with Spencer Krause is sponsored by SKA Robotics. If you're in the market for elite field robotics expertise, please consider hiring SKA Robotics. They sponsor this podcast and solve some of the toughest engineering problems in the world. SKA Robotics can be found at skarobotics.com. Tell me a little bit about some of the things, just to change the subject completely, that you did before you got into university. So I know you were in the Chilean Navy. You worked in like operations. You had some pretty interesting jobs over your career.
Oh yeah, it's a long story, but that's what we're here for, right?
Yeah, I got time.
So I was an officer in the Chilean Navy for 12 years.
Nice.
I wasn't part of the engineering corps, we call it somehow. I was an engineering officer. I served in the Navy on board ships, different kinds of ships, logistics support, training ship, fast attack craft, like just purely combat ships. I was also there as a salvage diver.
Is that where you learned how to dive?
Yes, I learned to dive there.
That's cool.
That was one of the many interesting and rewarding things I did there, like salvage divers. Back then, salvage divers were also search and rescue. Like nowadays, they've separated, but back then we had to do all things.
Why do you think they separated? Oh, sorry, I didn't mean to cut you off.
Oh no, it's okay. They separated mostly because there's very different tasks. Salvage and search and rescue. Salvage is mostly focused on material, like shipwreck, things that are lost, fall down, repairs. There's a lot of like based on taking care of materials.
Yeah, it makes sense.
While search and rescue is people.
Yeah, makes a lot of sense.
So the methods, the approaches, the training that you need are different. So I think it was a good choice to separate them.
Yeah, I guess that makes a lot of sense. That's just specialization of labor.
That's right.
Yeah.
But besides that, I got to do a lot of very interesting things from an engineering point of view, in terms of projects, upgrades. The good thing is you get to do a lot with little. Just think about it. This resembles to any ship, not just the Chilean Navy, but once you set sail, you're on your own. You are in the middle of the ocean, for example. Something goes wrong. There's no Amazon that will deliver a spare part within 24 hours.
Not even if you pay them extra money?
No. There's no chance that will happen. There's no tech support on the phone that will guide you through the steps to solve your problem. So it's you and your team that, based on the training that you have, the knowledge you have, and how you can adapt to the different circumstances, that will solve that.
Wow.
And that's a great experience. I call it field engineering. Like, you have to do engineering on the field with the resources you have.
Can you give me an example of like a field engineering story or something you had to?
Sure.
Yeah.
One that I'm very proud of that we did, and it was like a very demanding task. It was a long time ago. If you're not familiar with the Chilean geography, in the south of Chile, there's a lot of fjords, islands, very narrow straits where you sail.
Cool.
And we were sailing on our ship. It was a logistics support ship that goes every summer. It goes down the south part, which is very cold, but during the summer you can sail safely and provide support and take all the supplies that different regions need. So it's a task that takes from December to early March.
Cool.
And one night we were sailing through one of those straits, and the engine in this ship has a pneumatic clutch.
Okay.
It's based on air pressure. As long as you have air pressure, there's clutch, you got propulsion. And suddenly we had an alarm, low air pressure, and we informed the commanding officer, and we made our testing. We analyzed this. We could not repair it. We didn't know what was going on. And at some point, my boss, who was the chief engineering, and I was the second there, said, we got air for about an hour and a half more. That means in an hour and a half,
we're losing propulsion.
We're not losing propulsion. In an hour and a half, we lost propulsion.
Oh, wow.
There's no more propulsion in an hour and a half. And in those narrow straits that you're sailing, that means you're crashing somewhere. So,
oh my gosh.
Yeah, that was. So we had an hour and a half to solve the problem.
Wow.
And we split our team, and some people tackling the compressors, air pressure, and I worked with some of the guys, and we had a machinist on board. We had a lathe. We had a lot of like manual machines that could do some basic part repairs, stuff like that. And every ship has their own like fire. I'm gonna say like firefighting equipment, but that's firefighting equipment. So with air breathers and all this stuff. Turns out the air pressure we needed was the same that all the air breathers tanks held.
Nice.
So in this brainstorming of ideas of how to do this, it came out like, hey, why don't we build a piece that will help us feed the big air tanks of the clutch with the tanks of the air breathers? So we started discussing, we looked for the materials, then we talked to the machinist, can you build this piece? And he was like, yeah, it will take me like 40 minutes.
How much time did you have left at that point?
I mean, it was like 10, 20 minutes from that one. So we had time. And the guy was great. Like, he did it in even less than 40 minutes. He did it well. And there were we, a whole line of guys with the tanks, feeding this huge air tanks with this just single piece, putting the tanks there, opening there, filling the tank. And that gave us like an hour and a half more.
Nice.
While the other part of the team were disassembling all the compressors, cleaning pieces, looking for spare parts. And finally, thanks to that extra hour and a half we had, the other guys found the failure, repaired it, and we kept sailing.
Nice. What did it end up being? Like, what was wrong?
It was a failure on one of the valves of a compressor that was not making the proper contact, so the air was going out of there.
And that took the whole air system out.
That took the whole air system out.
That's wild.
And you could not find that failure unless you disassemble the whole compressor.
That's insane.
It was insane. It was, at the moment, it was a huge emergency, like, of because of what
Did you have
I
to
fly.
like steer out back into the like away from the fjords? Or did you just
You
not
can
have
know
enough
you
space?
you were already there, so it
You're
was
committed.
like you were committed to it.
Yeah, that's
We're-
wild.
It was wild. It was crazy, but we solved it. We managed it, and it was a nice job. And I say it's the commitment of the whole team to solve this was great. And
That's amazing.
It was like 2 a.m. when it started. We finished about 4:30, 5 a.m. So it was the whole night working on it.
Yeah, I mean you had to.
There was no other option. Sorry.
Yeah, no, for sure. And no other shop either. It sounds like you had to wake everyone up.
Yeah, but things like that, and that's what I say. Field engineering, like you have to solve the problems with what little resources you have right there. There's no one to ask for guidance or help. There's no
Sounds
one
like you
coming
asked
to
the
rescue.
machinists.
I mean, you have your team, right?
Yeah.
But there's no one external to
For
help
sure,
you on this.
For sure. That's incredible.
Yeah, and things like that happen.
I could listen to field engineering stories all day.
I mean, those things happen more often than not.
Yeah.
But
That's wild.
But it's
And that's why you have like a mill and a lathe and all that stuff on the ship, as people realize.
well, you don't have it on every ship. We were lucky that we had it on this ship because of the roles that this ship has to fulfill within the Navy.
So you're making parts for other ships.
One of the roles, I mean, it's a logistics support ship. So you have to provide logistics support to other ships, to communities. So that's why you have lathe. It even has like a small hospital inside. So things like that.
You say small. How many beds?
Oh no, it's like you don't have beds for the hospital. You have the OR. You have a lot of like hospital facilities, but you have the beds of the ship.
Oh, that makes sense.
Which
So
would count as beds for the ship.
Yeah.
But you have the
You have to save space. You can't have dedicated hospital beds.
That's the thing. It's not dedicated hospital beds, but you can provide hospital services like health services.
That's pretty incredible.
Yeah, those are nice things that you can get there.
Yeah, and obviously carrying cargo, I would imagine, with a logistics support ship.
Lots of cargo, and all sorts of cargo, from like food and supplies to cars and things like that.
Nice.
Yeah, that's one of the roles that that ship had. I mean, still has in Chile, and that's one of the things like I liked about it. Like I got to sail a lot. Like we didn't spend much time on our port, but I get to travel all around the country, like everywhere, meet different communities. It was a very, very nice experience, not just from the engineering point of view, which I just told you, but also from a personal and professional point.
That's incredible. No, it sounds great. I mean, and also like I'm kind of curious to learn more about some of the diving things that you've done in the Navy, but also since you left the Navy, it sounds like you've continued that part of your career. For
the diving, you mean?
Yeah.
Yeah, I mean, even though I learned to dive in the Navy, it's like diving is it's a way of life, I'd say. Yeah, it drags you, and you learn to enjoy it and appreciate it, and it's great. The freedom you feel when you're underwater, like just floating, it's flying. It's impressive.
That's really cool.
Yeah. I mean, every time I get the chance, I dive whenever I can.
Nice.
Even places that you would say, "Why are you diving here?" It's like there's nothing to look at. It's not because of what you see. It's mostly because of what you experience. That the sensation of floating, of being driven by the current, that's indescribable. Personally, it fulfills me a lot.
That's incredible. As someone who's never done it before.
Yeah, I mean, if you've never done it before, I strongly encourage you to try it.
Well, how do you start?
There's lots of like diving academies or schools that provide like the basic learning for it. There's lots of places that do this diving baptism, which is like a very simple intro to diving, and then just get you in the water with an instructor. It's very similar to like it's very popular now, like this tandem skydiving when you go like
that makes sense.
Very, very similar to the idea of that.
You're strapped to an instructor.
You're not strapped to an instructor, but you go hand by hand with it.
That makes sense.
I mean, after this strapped skydiving, you're not a skydiver. same thing. I mean, after this underwater baptism, you're not a diver, but you experience the diving.
Yeah. And you're hooked enough that you might come back and become a diver.
That's the thing.
Yeah. Well, do you have any like personal projects or kind of, product ideas or things that you're trying to pursue now that you're comfortable discussing in front of the whole internet?
Oh, yeah.
Because that's who listens to this podcast, the whole internet.
Wow, that's a great audience. Personal projects, I love what I'm doing right now. On this work on haptics, on developing these interfaces that will provide a better dexterous manipulation. And I think about like all the possibilities it has to improve people's lives. And with that last concept, that's what got me into robotics. Like, use robotics to improve people's lives.
Yeah, for sure. No, same here.
And I think that robotics has this ability to improve lives in so many ways. And I think that's my personal goal, project, you name it, and help use this technology to improve life, to make a better quality of life.
Yeah, I couldn't agree more.
And it's not just like autonomous cars, let's make roads safer, or let's make let's not need to drive and you could rest in your ride home. I think there's so many like little tasks that can improve your life that but using this simple robots, you don't need something super elaborate to make life easier or more fun. So that's the thing.
Yeah, that makes a lot of sense. Well, I feel like we're at a good stopping point. I think that's a lovely message to end on. So as we get to the end of the podcast, is there anything you want to plug? Like, just hug your kids, like buy stock in Google, apply to Carnegie Mellon.
Building on what I said before, like, there's a lot of hype on the impact of robotics and AI in the world right now. There's a lot of different points of view, opinions, fear, stress, interest. And I feel that there's nothing we can do like to stop it. Like it's as many people say, it's a train that already started, right? But I'm not going to use that phrase anymore because many people have used it, and it's like
I've never heard that applied to robotics.
Really? Yeah. I've heard it applied to AI and robotics so many times. But
I've heard Pandora's box. But yeah, anyway.
Yeah, Pandora's box too is a good example. But I'd say it's something that we can embrace and transform into an asset from any field. Like, it's like you're learning a new hobby. For example, let's say I want to start carpentry. Oh, I learned how to use a hammer, I have nails. But when I learned to use a hammer, everything looks like a nail, right? But there's also screws, there's glue, there's files. There's lots of different tools to use it. Same thing here.
Yeah, for sure.
It's learn it, but learn it properly, learn it well, embrace it, and use it properly. Use it wisely. Don't be afraid of using it. Don't be afraid of learning from it. Don't be scared of the possibilities, because it will open up many others. So that's what I'm saying. The final message to listeners or viewers or whoever's on the other end of this, prepare yourself to get to use and get the most out of it, because it can be an incredible tool to, once again, improve your life.
Yeah, I couldn't agree more. Get into robots, folks, if you're listening.
Yeah, definitely.
All right. Well, hey, thanks for coming on, man. Really appreciate it.
Thank you very much for the invitation. It was a pleasure.
Looking forward to the next one.
Thankfully.
Thanks for joining us today. If you've made it this far, chances are you'll like other episodes too. Collaborative with Spencer Krause can be found on YouTube, Google Podcasts, Spotify, Apple Podcasts, Pocket Casts, and Radio Public. Subscribe today to get notified when the latest episodes release and support the channel. Have an idea for a guest I should interview? Hop in the comments and let me know who that is. I'm always looking for new people to talk to, and chances are you know folks that I don't yet. Thanks for coming in, and I'll see you on the next one. Collaborative with Spencer Krause is sponsored by SKA Robotics. If you're in the market for elite field robotics expertise, please consider hiring SKA Robotics. They sponsor this podcast and solve some of the toughest engineering problems in the world. SKA Robotics can be found at skarobotics.com.